of course, when you take this neighborhood to be smaller and smaller, then this open sets become larger and larger. Then actually entropy will become actually smaller and smaller. Yeah, if the open sets become larger, then it's easier to cover the whole space. Yeah. So this number becomes smaller. So actually, one does not require that there is a uniform partial bound for these numbers. Yeah. When the neighborhoods shrink to the points x1, x2, this might go to 0. Yeah. But the point is that for no matter which neighborhoods you take, this is at each stage, this is always strictly partial.
So the limit of this number goes to 0. Sorry, there is a limit if you take smaller and smaller.
Yes, when this neighborhoods become smaller and smaller, this is actually gets a lot. This also gets smaller and smaller. So the limit is just the
there is a limit. Okay.
Yeah.
Okay. Yeah, it got smaller. Yeah, you're right.
Sorry, but does it always converge to 0, or are there examples where it's bounded below?
Other examples where it is bounded below? Not sure, but typically they should go to 0. They should really. Could there be some very strange examples? It's really there's a part of lower bound. Yeah, I'm not sure whether there are such strange examples, but typically they should go to 0. So then what Banach really showed is that actually the existence of such things actually characterize whether the system has partial entropy or not. So theorem E. He showed that system has partial entropy if and only if there exists entropy pairs. So in other words, you can say that the reason for us to having partial entropy is simply that you get this pair of points. They are the source, or they are the origin, or the reason for the partial entropy. They are responsible for that.
Is it the existence of one entropy pair, or is it equivalent to having infinitely many entropy pairs?
Yeah, that's a very good question. So next time we'll see that once you get one entropy pair, you will get a lot of them. Yeah, this is the only existence for just one pair. Yeah. Once you get one, you get a lot of them. Next time we'll see. So how did they prove it? Actually, this is based on two lemmas. One, the first thing is that the entropy is positive if and only if you get positive entropy for some very kind of like a special or open cover. Okay. And only if there exists A1, A2 close. Disjoint. So the picture is that A1, A2 just like this. No, they allow you don't need to worry about X1 and X2. Such that for you still in the complement of this set, the entropy is pi. So the original definition says that there exists some open cover such that the entropy is positive, but here it says that you can require to be of certain special type. Then the second step lemma says that once you have this, then actually you can find one entropy pair inside of A1 times A2. Yeah. Assumed. So still for U to be the same as here. Entropy is positive. And then there is this one entropy pair. X1, X2 inside of A1 times A2. That means X1 inside of A1, X2 times A2. So once you get such a situation, you can find one pair X1, X2 here so that this becomes one entropy pair. Now let me explain the proof of the first lemma. I guess it should be quite clear that lemmas B1 plus B2 implies 3. That should be clear. Now let me explain how to prove this one. This direction is obverse. That's trivial from the definition. Yeah, we just need to worry about this direction. So we're assuming the entropy is positive. What we do is the following. So if the entropy is positive, so there is one open cover. This finite open cover V such that the entropy is positive. But this one probably has a lot of open sets there. Yeah, it's probably more than just here. This means that you get exactly just 2 open sets, but this one probably have a lot of open sets. Yeah. What you do is that for an x, because this covers the whole x, so there is this closed neighborhood. Ax of x, such that Ax is contained in Vx for some Vx. Yeah. So this point is contained in some open set inside of this one. Then you just take a very small neighborhood, closed neighborhood in there. Now, these neighborhoods together will cover the whole space. But X is compact, so we can actually use a finite mechanism of them to cover the whole thing. Use X compact. Such that this AX1 until AXN already cover the whole X. But this AX1 is contained in some VX1, and AXN is contained in some VXN. So now we can set U here to be just basically the complement of this open set, this closed set that's open, and together with this one, they will cover the whole thing. X3, X. Now, if we take the joining of these guys, let's see, joining of all these of the this actually we will actually defines the way in the sense that this is one. This is joining of them, so this is one open cover. This just means that every open set here is contained in some open set here. The reason is that when you take the join here, what you do is that for each j you pick up one of these guys. Then you take the intersection. Okay, so if you pick up this one, okay, then the intersection is already contained in this one. That's fine. Yeah, so the only case to worry about is that for every j you take up this one here. Okay. But if you take up this one, then when you look at the intersection, I notice that these guys, before these closure sets here, they cover the whole thing. So when you look at the complement, the intersection is actually empty. Yeah. So this intersection, if you, for every j pick up this set, the intersection is empty. Then here you can take a negative. Doesn't matter. Yeah. Now there are two facts very easy to check. That is, if you have u defines v, then the entropy of u actually is not. Yeah, because u defines v just means somehow the sets here are smaller. Then it's more difficult to cover the whole space intuitively. Yeah, but this is very easy to check directly. The second fact is that if you have two open covers, then u1 joining with u2, this will be at most the entropy of u1 plus entropy of u2. Yeah. That's also very easy to check. Basically, if you have bunch of open sets from u1 to cover the whole thing, bunch of open sets from u2 to cover the whole thing, you just take the intersection of these guys. Yeah, then they already cover the whole thing. Yeah. So now from this facts here, what we can get is that we already assumed that V here has positive entropy, and this one defines it, so it has bigger entropy. Then the second fact, this is actually at most the sum of the entropy for each guy. So the sum of them is positive, so at least one of them is positive. But then this uj is what we're looking for. It consists of just exactly two open sets there. Any questions? For the second lemma, the proof is fairly easy. So what I will just mention very briefly, because later we're going to see some lemma in the combinatorial situation, which actually implies this one. So I'm not going to see the detail here. Yeah, what you do is that when you have such a situation, you cut A1 into two closed sets there. Then you can see that if A1, A2 satisfies the condition here, that either this closed set together with A2 satisfies this condition, or the second closed set here together with A2 satisfies the condition. Okay. So it's kind of like a Ramsey situation. If you cut this into two, at least one of them will still be good in the sense that this condition holds. Yeah. Then you cut, then later you cut A2 also into two pieces. When you cut it further into two pieces, going on, eventually this closed sets shrink to a single point. Then that is what we're looking for. Then repairs. So this is Banach's result. It's kind of nice because originally the entropy is defined, topological entropy defined globally. You have to look at the whole space. Somehow here you only look at those 2 points. Okay. Yeah, it's kind of a local situation. Yeah, it's more concrete, you can say, you can feel. Yeah. However, if you really want to use it, it's not so convenient. The reason is that in the definition of entropy pairs here, this definition here already uses the topological entropy. Okay. So if you want to really use it, you're coming back to the definition of entropy. It's not really so easy to use. Okay. There are basically 2 ways to use the solution. One way is actually goes in through the algorithmic theory. So what you do is do kind of a variational principle. For every invariant measure, you try to define entropy pairs for that invariant measure. Then you prove kind of variation principle that the entropy pairs are basically union of the entropy pairs for the invariant measures. Okay. Then when you go to the concrete, look at the specific invariant measures, especially algorithmic ones, then you can use the tools in algorithmic theory, like Pinsker factors and like that, to get results out of it. Yeah. Another approach is to do it directly, not going through invariant measures, just using combinatorics. That is what we're going to talk about here. And so, let me describe the combinatorial notion here. So let's V1 to AK. This be a tuple of subsets of X. And now, if you have a non-defined subset of the group, this is called an independence set. For A, if what you get is basically a situation like the full shift. So if for any sigma from F to 1 to K, then this a point such that this point will go under the group elements in F. Under action, they will go to one of these sets as we specify using this sigma. So S X sigma will be contained in a sigma S for every S. Yeah. Let's just look at one example. If you take F to be just simply just 3 points, what we do is that this is, for example, K equals to 2 here. So this will be A1, and this is A2. Now you think about that you get several copies of A1, A2. Then this X sigma here will go to, for example, if you want under S1, you go to A1, you can do it. Under S2, you want it to go to A2, you can do it. Under S3, you want it to go to A1, you can also do it. Okay. Yeah, no matter which way you want them to go, you can always find a point to do that job. This name here was also called interpolating sets by some people earlier. also used in some papers. One example to keep in mind here is that just for the full Bernoulli shift. So if you take x to be 0, 1 to the gamma, that means the finite set is just two symbols, it's just 0 and 1. You take here AJ to be the points, where at the identity element is simply just J for J to 0 and 1. Okay, so get two sets here. Yeah. In this situation, only F non-finite. This is an independence set for A1. The reason is very simple, that you want find you want x to satisfy this condition here, so x to be inside of a sigma s for every s. You want to find such point, then this really simply just means that if you look, because this really to say this the value of this point at the group identity element is simply just equal to this number. So this is really just the same as to say that x is actually simply equal to sigma when you restrict it to f. And because we're looking at the full shift, of course, we can find one point satisfying this condition. Maybe it's time to take some little break.
5 minutes, maybe.
Yeah, 5 minutes.
We need to restart the computer.
Passare. No, non
Started for this.
Ah, pure a me si è io sto...
Continue with the second half of presentation.
Okay. So this definition for independence sets. Now we're going to look at how large is the independence set. But, how do we characterize that? This actually could be interpreted in various ways. Here we're going to just look at the density of the independence set. Okay, so this is what we're going to do. So we look at a k-tuple of subsets of x. Then we're going to define a function phi a from non-empty finite subsets of gamma for real numbers. So it's going to be defined in this way, very simple way. Just look at the independent sets there. So this will be defined as the maximal size of k, where k is contained in f, and is an independent set. Set for A. So we'll simply look at all subsets of f being an independent set for A. Look at the maximum size here. Yeah. But it's easy to say that if these guys are non-empty, then actually every single point is always an independent set. Okay, because you get only just one. You get only just one. Well, if you get only just one element here, then of course, from this condition, you can just find your x if this is empty. Yeah. So maybe I just say put it here that each of them is non-empty. If one of them is empty, then this actually will always be zero. There is nothing interesting. Then this actually function actually satisfies a bunch of nice properties. The first thing is that actually it's right invariant. Yeah, so when f gamma non-empty finite and this in gamma. The reason is just that simply a that's right. Yeah, simply just that K is an independent set for A if and only if K times S is an independent set for A. That's something very easy to check. So you get that actually you get the same value here. This is right invariant. The second is that the so-called Shear's inequality is satisfied. So for any f in gamma non-empty finite. For any E here, this will be a set of non-empty subsets of F. Here we allow repetitions, so strictly speaking, it's not really a set. I mean, we allow that two members of it to be actually the same. Satisfying the following condition. So you take the sets here, you treat they are all subsets of F. Just count how many times they cover F. Yeah, the condition is that they will cover F, every point of F at least m many times. So E here, this will be at least m times the calculated function of F. Okay. So that means every point in F is covered by the sets here at least m many times. So under this condition, one finds that the value of F is the sum of the value for E, where E is inside of the set here, adding together and then divided by M. So, or you can just write it on this way, probably better. Yeah. So if they cover F, every point of F m many times, when you take the value here, it's also at least the value of F multiplied by M. So the proof is quite straightforward. The reason is just that if you take, so we take K in F, independent set for A in the maximum size. So that means the size of K is equal to the phi AF. Then for every E, we just take the intersection with K, that will also be an independent set there. Yeah, so for any E, the intersection with E is an independent set. Because if one independent set, you take a subset, that's also an independent set. But then this tells us that the phi E would be at least this intersection. The size of the intersection. Then we get to that if we take the sum here. Then this would be at least the sum of the intersections. But what do we get? Well, we're just simply counting the number of points in here, but for each point in K, because of this condition, for each point in K, particularly it's in F, so we know that it's covered by E at least M many times. So then this will show up, this point here actually will show up in M many E's. So then we get that this will be at least M times the size of. So then this is simply just the phi A of F. So that is what we want.
What was that? N is M. N is M. N is M, I think, all the time.
The M is here, so just any particle number. And the particle integer. Satisfy this condition. Questions?
One is for all M and N? This thing is larger than M times 1 for all M?
1 times here, the calculation.
Yeah. For every M.
Not for everyone, just if whenever we have F and E and M, satisfy this condition. Make a second, right, satisfying after here. That's better. Once we have the two properties, the main thing is consequence of it is that then the limit for this value divided by the size of f actually along the Fourier sequence it will converge. Actually, more than that, actually it converges to the infinite value. So this is along the given Fourier sequence. The limit exists and is actually equal to the infimum over f here. This is non-empty, finite, and subsets of gamma.
Sorry, the function phi is also subadditive or no?
Subadditive. It is subadditive, yes. But subadditive does not guarantee that it's equal to the infinite. Subadditive will be guarantee that it satisfies that the limit exists. So one can apply all them are here, but you only get the limit exists. You cannot get that it's equal to the infinite.
Excuse me, it's just phi or phi A?
Phi A, yes. explain why this is equal. This is true in a moment, but let me just say that then we can define the independence density for A to be simply just this number. That's a bit. Now let me explain why the limit exists and equal to this, mainly y is equal to this inf. This fact is quite useful. So here, this is due to on the north. No need. This is that when the function satisfies this first two conditions, 1 and 2, then the 3 holds. So let me explain it. The proof is fairly simple. So let me explain it. So in one direction, what you have is that the naming on the left-hand side at least the right-hand side. Yeah, this is trivial. Okay. Then we just need to show that the lim soup is at most the infinite there. So at k namely finite. Then we're going to construct some family of sets E here for each Fn. This is going to be K S intersecting with Fn, where this is in gamma, and the Ks intersecting with Fn is going to be 9. Yeah, because here we wanted to be 9 sets and contained in F. So here this is going to be contained in F1. That's why we pick the intersection. Then, if we take the sum of these guys, look at all these sets together. Yeah. Then they will cover each point of Fn exactly just the size of K many times. Because for each single point here of Fn, you can try to use one point in K times some S to cover it. Exactly just one S there. Yeah. For each point here, for each point in K, you can use one S so that the product here is equal to that point. Okay. So you put them together, you see that you cover each point of f exactly just the set of k many times. So then we are in a situation here with m be just equal to the size of k. So condition 2 implies that phi of fn will be at most the size of k divided by times the sum of phi e, where e is in this e. Another hint for any numpty d gamma finite, we can also construct some e there. We can e to be simply just each single point in D. Okay. Then what we get is that they will cover the points in D. Each point is just exactly just once. Okay. Of course, that's trivial, but then one can use it to get some control of the value of phi on D. So the condition 2 here will implies that phi of D at most the sum of phi E is here. But what is this saying? This is simply just phi of this singleton S, where S is inside of D. But these guys are actually all the same by the condition 1 is visited because this singleton actually you can multiply one of them by some group element to move it to the other. Okay. So this will be the same as D phi D. Get the control here. Now we can put them together to estimate this one here to get the upper bound for it. So here we are using the condition 1. F1 will be the size of k here. G. Now we're going to split it into two pieces. One is that actually this is completely contained in F1. The other case is that part of it is contained in F1, but the part of it is outside. So every E here is of this form. Now we're looking at the case where this is completely contained in F1. The other piece is that this is gamma Ks intersects with F1, but the Ks also intersects with the complement of F1. So it's not completely contained in F1. Now for this one, this is because it's completely contained in F1, so there's no need to take the intersection. That's simply Ks. And by the first condition, this actually one can remove S because it's a relative invariant. So here what we get is K times the number of S here. For the second term, one can say that this would be just applied. You take D to be this set here. One can get that this is at the most. This at the most. The size here, that is D size here times this value. This is for each such S, but I should say that here I should put the size of this one here, but I'm going to make it larger to be the size of K. But I need to worry about that maybe this is negative, so I'm going to take the maximal with 0. And this is just to take care of the case that is actually negative value. Then we look at how many S here we get. Now we can just divide everything by the size of Fn, then take the limit. So this tells us that divide everything by the size of Fn. We divide by the size of Fn. It's well known that this just becomes just 1. Okay, this guy divided by the size of Fn. That's just the formula that is Fourier series. And this number here, this is a boundary basically. So this one divided by the size of Fn will go to 0. And this is a fixed number here, so the product is also 0. So that finishes, this is a proof of this lemma here. Questions? This is the definition of independence density. Now we can give the combinatorial description of entropy pairs. So we're going to see that a tuple x to the k is a tuple. Here I means independence entropy. If for any neighborhood Aj of xj, so each one will take one neighborhood there. This tuple, by putting these neighborhoods together, has independence density strictly defined. So that's the definition of Irish tuple. The point here is that in this definition is purely combinatorial because the definition of independent sets is purely combinatorial, and for the density is you can also for density is visited. You could either describe it as a limit or describe it as an inf. Okay, so in the definition, one does not mention the topological entropy at all. But then it turns out that this actually turns out to be basically the same as the entropy pair. But before that, let's look at one example. Okay. Yeah. For any maybe compatible travel today. And we look at x to be the flow shift. Yeah, shift action is defined basically as the same as before. Earlier we mentioned the case Z is finite, but for any combinatorial space you can do the same thing. In this situation, every k tuple k is actually one item. The view then is very simple. So given neighborhoods there, A1 until AK, one can easily find K number finite. We know that you can shrink it to be an open neighborhood, then you can see it at the finally made coordinates already. Yeah. So that for any j, if you have y equal to xj on k, then this implies y is already inside of aj. Okay, so we're saying that if y is the same as xj on the finally made coordinates, then it's definitely inside of this neighborhood. Once you take a k large enough, you can do this. And you can choose the same k for every j. Yeah. Then, when gamma equal to z, one can say that this aj is A1 until ak has part of independence density in the following way. So let's just say make it k larger, say from -1 until n. Okay. Then this is 0, this is -1, this is n. So this is just the k. Okay. And here you can put shift it by some number. So this will be n plus 1. So what you shift it is just 2n plus 1 plus k. That's the length of 2n plus 1 is the length of this interval here. Okay. Then the next one is you get another copy of k. So 2 times 2n plus 1 of k plus k. Okay. Going on in this way. Now you want to specify the y to be basically inside of aj. Say on this part it's basically in aj1, this part is in aj2, this part is in aj3. So what we need to do is just that you take y to be the same as xj1 here, and the xj2 here, and the xj3 here. And for this, I mean that you shift it. You need to take y on this part to be actually the same as xj to restrict it to the original k. Yeah. So then this will guarantee that in this way you see that there is a point. I mean 0 and this point and this point. This point actually is an independent set. 0, 2n plus 1, 2 times 2n plus 1, going on, and define in many coordinates. This is actually an independent set for A1 until AK. Yeah. Now you can take bigger interval as the further sequence, further set. Then you see that you get a density at least 1 over 2n plus 1. Any questions?
This is a proof for gamma equal to z, right?
Yes. Okay. I will say what happens for general minimal group, how you can handle it. For any minimal gamma. So we'll look at NAF gamma 90 finite. So what you do is that you take a subset f prime of f, maximal subject to the following condition, subject to that k times the sets here, the points here actually are pairwise disjoint. KS1, KS2, KS3. Then you can find y basically the same, pretty much like this. You can make it y to be basically the same here as the xj1, xj2, same as xj3. Okay. Yeah. So then you see that what you get is that f prime is an independent set. A1. But how large is f prime? We need to know f prime, the size divided by the size of f. What you do is that for any t in f, because f prime is chosen maximally, so there must be some s in f prime, such that ks intersects with kt. But then this means t actually is contained in k k inverse ks. Okay. Yeah. Then we get that this is an arbitrary point in f, so f is contained in k inverse k times f prime. So this tells us that the size of f prime divided by f would be, maybe just put it this way. The size of f is the size of k times square times the size of f prime. Yeah. Then we get that the independence density, at least the size of f prime divided by f, you take the infimum there, this will be at least 1 over the size of k squared prime. Questions?
I don't see ways why we can take f primes such that the ks are paired with students.
Why we want to do that, or why we can do it?
Why we can do it?
This is just a final set. Just keep adding to it. You start with 1 point. If you can find another point, so that the case is still disjoint with the first one, you just add this point to it, to f prime. You keep adding to it.
It is always legal to take a singleton as f prime, and then.
Yeah, then you look at all the other points in f, whether ks is disjoint with your ks1 or not. You start with s1. You look at s2 in f. You ask yourself whether this is disjoint or not. Okay, if it's disjoint, then you just add s2 into f prime. Okay, then you look at the next one. Okay, until you cannot add any more points to it.
Can it be a situation when you cannot fit any shifts of k inside f, and so f prime will be need to be empty? Is it possible?
Empty? I'm not requiring ks is contained in f. I'm not requiring that.
Ah, I see.
Yeah. Right. So now we state the theorem. That is the entropy pairs exactly the same as non-diagonal IE pairs. Yeah. I'm putting non-diagonal because in the definition of IE pairs, we allowed the two coordinates to be the same. Okay, so pairs just means k equal to 2 here. Yeah. So we defined tuples, we allowed arbitrary k there. Yeah. So that means when we define IE pairs, we could have two coordinates be the same. But when we define the entropy pairs, they must be different. Okay, so that's why I had to put non-diagonal there. But this really means essentially they are the same thing, right? If you ignore this diagonal condition there. So this was proved by Wen Huang and Xiangdong in 2006 for coming to Z. Yeah, they used the allegorical theory method, pass to environmental measures, look at the repairs there, they use then physical factors in that to get it. Yeah. Then there's David Kerr. We showed it for any amenable gamma and using the combinatorial method. Yeah. Okay, I guess I should stop here. So next time I will see what is the combinatorial name I used for the proof here. What is the case there? Yeah. Thank you.
Any questions?
So if we take a pair, which is an entropy pair and also an IE pair, is there a relation between the independence density as a number and the topological entropy of the covers associated to the pair?
Yes, so there is one bound between them. One can, yeah, I was see in the proof of this actually in the proof of say the right is contained in left. Actually, one has to use that. Okay, so what you can see is. So in this situation, like we're cared about, so this is A1, A2, right? So A1, A2 closed and disjoint. And we're looking at the open cover consisting of the complements of them. Yeah. So in this case, one can easily show that the topological entropy here will be at least the density for independence density for A here. A is just this pair of closed sets times the logarithm of. So if this is positive, you get that is positive.
If no more questions for now, let's thank Hanfeng. And we have a break till 11:15.